Welcome everybody. Try Joseph here with you. Regards to all those who took part in this participation. Abrek Emmanuel Agabadorek, thanks to you all. Well, today we're going to look at a simple approach to our projects, that is knowledge distilled large vision model for accessible gait-based screening of skeletal disorders. For reference, here is our group code, SWAI 18. So what we shall be discussing today is specifically within this range of aspects, ranging from a background introduction, rated works, how other people have done it, problem statement, until when we shall reach out to limitations, conclusions, and then many more. To begin with, we should look at the background information behind the knowledge distillation approach to gait analysis. What happens in this context is taking in a case scenario, Africa as a continent, we have too many patients with barely recognizable gait infections or disorders that go unnoticed and get to be discovered when they are hard to handle. Now, in this case, therefore poses us into a case where we have a problem at hand. So, taking you forward, we shall be discussing more on aspects like what gait analysis means, what large vision models mean, skeletal screening, knowledge distillation itself, clinical embeddings, and then resource deployment. This will all be covered in the next slides more and more. Related works have been done, and a few papers have been quoted. For example, the Codiro ETLA of 2025, they use the synthetic time series approach to their gait analysis scenario, and then they also had a synthetic data fidelity of 97.9%, with given some other limitations. Many more papers were referenced, as we shall discuss more and more. Well, to begin with, I want to drive you to what problem we have at hand. So, as it was said earlier, skeletal diseases such as Parkinson's disease, osteoarthritis, and many more manifest within our Ugandan population, where we have a limited number of specialists who can handle it alongside very few laboratories which can accommodate our large populations. These signs go unnoticed and then go to be detected in later times. Why? In the early stages, they are very subtle and very hard to recognize patterns that need in-depth analysis to be able to recognize and categorize the different types of disease and flag them as early as possible. So by using gait-based screening system, therefore implemented a case scenario where all the different stages of a given disorder can be recognized as early as possible, and then further recommendations and preventive measures can be put in place. So, in trying to achieve this, we had a simple research on how to achieve it best. Well, our proposal was to implement a teacher model that goes in depth to look at the different gait patterns, but computational limitations in our state. We also went ahead to see how we can pass the knowledge learned from a teacher model into a more simpler, computationally friendly model. that will use the teacher as a basis of its knowledge to learn more and more and be able to work on edge devices used mostly in our population. Well, with all that, we have to think about implementing it practically with knowledge distillation framework to achieve a mobile-friendly system that can perform on end users. A simplest architecture goes on screen here, where during training phase, we had a source of our dataset, which was a private cloud backed up. Its details were converted into a CSV file leveraging the presence of tools like OpenCV, just for exploratory data analysis, like analyzing the time frame of each video, how many videos per given class, and many more, just to guide our processing. The same videos are passed into a teacher model, which gains insight about them, processes its knowledge, passes probabilistic distribution, what it predicts per class to its student model to guide the student's learning. The student also is also guided by the knowledge passed from a clinical BERT encoder, which passes a vector representation of a given clinical description of a video to guide the learning of a student. The obtained student is later containerized in a Docker instance and then deployed in a render application. Front end for user access was developed and also deployed on Verso. A communication was established using an application programming interface. Later, a sort of a confidentiality in health matters, we implemented an authentication system where a user logs in and performs all the kind. Well, there's much talk about this in the preceding slides. A similar methodology here goes in depth where we performed some downsampling techniques just to ensure that uh, the number of videos per class kept selected in each batch practically matches and be able to looks to be enough for model learning. Each video will have a frame representation which looks like a slides extracting frames per video. So each video will have a number of frames. These frames are later encoded into numeric representation by obtaining its position embedding vectors, and then many more. Later passed into an encoder, and then passed through a layer of neural networks. The knowledge obtained from the under layers are then passed into upper layers and to adjust the weights where necessary. This will be in depth discussed in the preceding slides. Uh, a simplest mathematical representation of how it looks like is this. Uh, the multi-scale autoencoder model, one of our model instances, uses self-supervised methods while learning, where a video is processed into a number of clips. Each clip has an embedding representation masking its visual explanation into frame height, width, and channel size, in which is later fed into a linear propagation to achieve a vector representation, and then later passed into an encoder to process uh, uh, the tokens, and then to create a contextual representation of a final frame. This is later masked, some features masked like uh, covered, lowered, and their visibility assumed not to exist. And then we tell our model, kindly tell us what was missing in this point. Uh, While decoding, it will now try to adjust its weights to see, to try to fill in the missing gaps with the knowledge, deriving its knowledge from the seen values. We therefore calculate its loss, how far it has deviated from expected results, and then adjust its weights while learning. And then this is how mathematical it goes in simple terms. Well, a simpler architecture, just like a previous one, is on here, but I'll go in depth to explain how model 2 looks like. Our video dataset source is fed into our teacher model, which later learns and then gives probabilistic distributions, which are passed into a softmax function with a high temperature to achieve knowledge, which shall be guiding the student model while learning. Student model through the hope of knowledge derived from uh, BioClinicalBERT, which processes clinical embeddings achieved from literature reviews of how this disease manifests, helps our student model to learn. As it learns, it compares what a teacher said each video to be. The knowledge happens recursively until we achieve a more sophisticated student model able to recognize different gait patterns and ready to work in end devices. A more in-depth explanation of how a multivision transformer looks like. We have an input image which is derived from a frame in a video. It therefore achieves a patch representation embedding into what it looks like in each instance, like its definition per itself, how it appears in the other frame, and then many more. The multi-heads of attention now breaks within a frame, we attain smaller patches of each frame and then processed individually. Each frame, each small patch in an image is processed individually in a multi-heads of attention layer. This is later fed into a multi-layer perceptron block, which now combines the knowledge from all the different smaller kernel-like, just like a kernel equivalent in a CNN. To, the knowledge is now combined in a multi-layer perceptron block, and then attention pooling is where we study the relationship between each image instance with the related images within a given video. Therefore, by so doing, we shall achieve a long-term dependency. We shall be able to achieve long-term representation. We shall be able to see how long-term dependencies vary in each video. This is a layer which happens recursively. The same block happens after the attention pooling. It again goes back to the multi-layer attention, the multi-heads of attention, recursively, until when we achieve a classification head, which we then pass into our student model through a softmax function converting into probabilistic distributions. A simple representation of how our large language model, and that's BioClinicalBERT, looks like. It takes in a clinical text, converts into tokens, how each word in a sentence looks like. Its representation of each token is now how a token is its individual meaning, its contextual meaning, and then its position definition. This knowledge is what is passed into a pre-trained BioClinicalBERT, which was trained, and then it learns the simple patterns within each word and then achieve a vector representation in a linear form. So we shall have a token representation which can be used for other tasks like named entity recognition, recognizing objects or humans or named entities, a classification task, and many more. But a achieved vector is what we shall use to train our student model. So basically, in the attained data sets, CSV file, this is how distributions within the database, within our videos looked like. We had uh, imbalance in our data set, but using downsampling sampling techniques, we were able to make sure that each class is at least represented in each batch instance passed into our large vision model. This was done by increasing the most likely occurrence of underrepresented classes like the Parkinson disease, severe, the assistive, and then the non-assistive, then lowering the probability of highly represented classes. The duration was almost the same, just as illustrated here per a video for all videos in the different files. And then the correlation matrix represented how the different diseases, how the different uh, uh, aspects within a video correlated, like how each was, like how each disease, like how each gait pattern was associated with the other. So we found that there was no relationship between others, and they had negative correlation as indicated by blue colors. And then those red colors represented some positive correlation where a dependence between maybe the limb, the stride length, like that, depended on the other as illustrated. A simple a scatter diagram illustrated that there was overlapping between the different types of diseases, and a sophisticated approach needed to be able to classify the long-term dependencies within our data analysis system. A simple results and many more. More interestingly is our results. While when we trained our multi-vision transformer, we achieved a loss of 49 with accuracy of 86, precision 86, with recall of 86%, F1 score of 85%. The validation results also showed 70% on validation, and then 70% on testing. A simple classification report per each class also still showed that given sampling techniques worked to create balance within each batch representation per class, there was still some classes that weren't picked, as seen by a PD, a severe, based on the knowledge achieved on how these diseases, how videos, the number of videos were. We saw that PD severe had very few videos, and even in some testing, it therefore shows that it didn't appear in some of the batch samples that were picked in model training, and it therefore had a 0% precision, recall, and F1 score. To go forward, this is a simple illustration of how deployment went on. We had development locally, pushed, Dockerized, and then pushed into Docker Hub, hosted on cloud, which an API was established through Verso, and then now users were able to access our front end, which simultaneously communicates with our deployed gaitAnalysis system in a cloud hosting company. This demonstrates how it looks like being in our system. One, for confidentiality, one can log in, then you can upload a video. Uploading, processing goes on, and analysis goes on. A predicted disease with a percentage confidence is then displayed to the user, and then this can be more explained using a clinical expert who can then give more insight on what to be done. Computational limitations, basically during training, we had limitations. Our models we're using were resource intensive, more specifically MVIT. It needed GPUs or TPUs for its training, which we leveraged using the present tools, using Cargo and Colab, we were able to train it simultaneously. We therefore conclude that in this project we have demonstrated how complex gait patterns can be handled in a more simple and simultaneous way using our large vision models. We therefore uh, be able to achieve efficiency by bridging the gap between the few orthopedics in the country and the large number of users by using our AI system to to ease their work, be able to analyze diseases and classify as early as possible. I can't